So which topics?
I wanted to learn about atom, the
Atom model,
atom
atomic
thing.
model?
Yeah, in like the atomic spectra.
Yeah. How do you explain atomic spectra? Yes, that's right. You can share the screen. And so there are two types of spectra. One is called absorption, another called emission. Do you know the difference between these two? One is,
Absorption when
yeah,
they absorb energy and emissions when they emit
yeah.
energy.
By what? Absorbed by
Um,
what? Emitted by whom?
so the atom
Hydrogen
energy state.
atom, hydrogen atom. Yeah,
Yeah.
yeah, that's right. You're right. So one is called absorption. I'll just write this at this corner. And absorption. Yeah, that was observed in 19th century. Absorption. Another is called emission. So that's why you are right. Emission is considered the energy emitted by the hydrogen emission. Okay. So the difference is that if you basically you have to consider spectra used, right? So you have to consider the source. So if you have the source, and the source is cover different frequency, among other things, you got rate. You see, just very briefly. So this is a continuous. It's continuous source. So spectrum of you have first use a proper source like the sun. Okay, the sun have the because Newton first discovered that the sun ray actually is contain different colors, right? So this different color, and then eventually we realize this color is due to they have different wavelengths. If we use model of electromagnetic wave, so that is wavelengths were determined their the wavelengths will determine the color of each component. Right? Last, can use purple here. So that is a source. You can imagine this. This first one is the sun spectrum. Okay, the sun as a source. Sun as a source. Okay. So what you actually do it? Because the Newton first did that experiment. They just let the light ray go through the gap, right? It was a very small gap, so that is the direction of ray. And then what they do, what Newton did is just put the prism here, prism like this. Can you see? Like a prism here, prism. Okay, so that is also made by glass, and by using this simple device, optical device, Newton first discovered that you will see the different color, right? I just draw some of them. I just don't have to draw. So the sun can be the ray can be divided into, among other things, the red here, and the green, and the purple. I jump now. Can you see? I just draw some of them. Of course, these regions called visible. That is only visible. Can you see? These called visible spectra of electromagnetic wave. This is the visible spectra, visible light. So this is so that's how, of course, apart from waves, you can argue that there are others, the sun ray even go beyond the rate called infrared, right? And you also the ray, invisible ray, you can go beyond the purple called ultraviolet. See, so that is called UV. This is UV. This is called infrared. Give some background would be help you to understand what is this phenomenon. So this is sun. Okay, when Newton did the experiment, he's interested to know to discover know what is the components. Okay? In this way, they can see the components of the ray. from the sun. However, in the 19th century, chemists and also physicists are curious about use this method to start different chemicals. Okay. So what they did is just put the liquid or gas, rather liquid or gas. Okay, you can consider the gas. It could be liquid. Okay, they put they put the liquid in between or the gas. Can we just consider the gas? Say the hydrogen. See, because hydrogen is the simplest. So everyone have to study hydrogen. So they put the hydrogen here. Hydrogen, chemically speaking, is just very simple, right? Easy to burn. You can only describe chemically say easy to burn, right? Hydrogen can form the hydrogen bond, and that's it. Okay, there's nothing you can see. You can say, right? However, what happens if when the experiment is used in this way, so we're talking about hydrogen here, and what would happen is that so in this this is a sun ray without, so this is a source without a sample. Can you see that is a without a sample in between. So this is called a sample. This is called a sample. When we do experiment, this is our sample. This is the sun. You see, it's the sun. Okay. Of course, eventually, people is different source, light source, right? Artificial light source, like electrical light lamp, okay? But you can imagine this is the sun. So what happens is that they say, well, this spectrum looks the same, except, can we just put the absorption together? We don't have to draw it again. For the hydrogen one, you will see something like this. I'm sure your textbook will also draw this diagram, but they didn't explain much. Can you see the dark band? Can you see? Can you see the dark band?
Yeah.
And that means that originally got some the light components, but this is missing. You see, so that's something very strange. That's and this can we call this can we label them? Oh, by the way, this direction. So this direction is wavelength. Wavelength increase. Wavelength you can either use nanometers, okay, or you can use any other numbers. Say, so are you familiar with this number? It's called angstrom. Have you seen this symbol in chemistry? Not yet.
No.
No. So that is this called angstrom. Angstrom is equal to 10 to the power of -8 centimeter. So it's, you in some books the chemistry text we still use this this unit, but doesn't matter. You can nanometer. Okay. So what happens if we label this can you see the number? Can we call this number lambda? So this is number 1. Can you see? So lambda. Can we call some lambda? Put some name here. Can we say this is 1? Can you see? 2 and 3. The 3. Okay. So that is so this is like a barcode in the supermarket, right? The emission, I just simply show emission. Emission, on the other hand, emission is such. Can you see it correspond to the notation? You will see this band. Can we just I chose purple a purple color for that. Can you see that correspond to that absorption dark band? Can you see? Except that this time it's actually getting only this position you see the bright, you see the photon if you want to know. However, others just black. You see, and so that is can I draw last one? Can you see these emission and absorption have same structure for the, if we use hydrogen atom? You see, they have same structure. So that has been the puzzles for decades in the 19th centuries, because in this way also people have found the helium by using this method. Okay, and that's why that is another story. But today we'll focus on how to explain this emission absorption. Basically, this lambda is the same. The wavelength is same. Okay, lambda 1. This is 1. This is lambda 2. Can you see? Lambda 3 and so on. And how do you may ask, how do we determine the emission? Well, emission have to go sideways. You see, you go that way. You put a prism here. In this way, you can avoid the background. Can you see that you can avoid the source spectrum? Can you see that?
Mm-hmm.
So if basically you have make an angle here, you have you choose a proper angle. In that case, in that way you can measure this spectrum. Okay, but in at this stage, what we are curious about this? How can we calculate this wavelength? Can you see?
Mm-hmm.
And for hydrogen, in the visible region, the most famous, so this group is called Bohr series. Have you heard of Bohr series? Bohr.
A bit, yes.
Yeah, Bohr series. There are other series. I'm talking about that. Bohr series. And this is the most famous one. Among other things, I had just read down here, they had Niemann, some people call the Niemann, they got a Niemann or Niemann series. And in addition, you got pop, called the pool, they call the pool or pop, doesn't matter, pushing series, okay? So these are also, the name Niemann and Pushing is started off the visible light. So we will, in most textbook, we talk about the Bohr series, okay? And Bohr is not just chemist, he also the physicist. So therefore he said, well, he actually, Einthoven was used a simple formula to describe what happened, what's going on. He just used a constant, right? Multiply, have you seen the number? So they use if you use a proper name, so that is n squared, and this is n squared minus n squared. Can you see? So that is called the Bohr's formula. It's Bohr's formula. You see? He's very clever, and this, if by just use one constant, they can model this series. Is that clever? He's very clever.
Yeah.
Right. Of course, he didn't know what's going on, but he can use this formula to describe it. All right.
Mm-hmm.
And of course, after that, there's another clever. Well, actually, I think he's a student or somehow. He's called. You know his name is called. Rydberg. That is the name, German. And Rydberg's contribution is that he rewrites the Bohr's formula. Can you see? Instead of looking for the lambda, his formula is use reciprocal. Can you see?
Mm-hmm.
He just uses change somehow because he thinks that is more meaningful. Of course, neither Bohr nor Rydberg can explain the origin of this barcode spectrum. Okay, so if you use this one and this formula changes slightly, can you see this formula became something like so something like this. Then he just put people remember him by using his R for Rydberg, you see. So the formula eventually becomes something like this. That is for the Bohr alone. So they have put this 2 square, take this n square. You see?
Yeah.
So that is this code. Of course, after use that one, and eventually, so Rydberg contribution is enormous because not just describe the Bohr's using the formula. Actually, he can define a Niemann series can also be explained. You see, this Niemann, this can call this Niemann formula. So that is a Niemann. So he said that, but Niemann's formula is simple. Niemann formula will be, can you see, 1 square take n square. Can you see that?
Yeah.
How about the third guy, the Bohr or Paschen? Okay, the Paschen, German is also German, and so he got the third formula. So that's formula. So for the third one, and the formula is still the same, except you can see the number changes slightly from 3 square takes n square. Okay. Did you know? Did the teacher tell you this formula before? or at least Rydberg, can you see? Did the teacher mention the Rydberg formula? So presumably that is formula for Balmer. So Rydberg rewrote Balmer's original formula. Okay, so that's why I think that is Rydberg. You see, and in general, so if I prefer to try to write a general formula for Rydberg formula before we go to the explanation. So in general, based on these ideas, so Rydberg's formula can be written as this: 1 over lambda n can be written as the constant multiply this factor. One is m squared, another is n squared. You see that? And m equal to 1, 2, 3, and even 4. Okay. And n is larger than 1 because n is larger than m by one factor. You see. So in other words, in this case, n is larger than 1. So therefore n is equal to m equal to m plus 1. Can you see? M plus 2, and so on. So with a little bit of math, you know that this is a very versatile formula. It can explain all theories observed experimentally. So that is due Rydberg. Okay. Understand now? So all wavelengths detected by hydrogen atom, there are hundreds, there are dozens, several dozens of them, can be explained by this formula. However, why this happened? So that is a question to be answered. People could not answer the question until the year when, but I think Danish physicist Niels Bohr. Okay, so Niels Bohr had his idea at the age of 23. Is that young? Yeah. Are you interested to become a physicist?
Nope.
No, thank you. Okay, that's 1923. You see. Now, what happened before him is very important. Is a New Zealander, it's Rutherford. Okay, you know the Rutherford. Have you heard of Rutherford in a textbook? So he has made. He's a student of J.J. Thomson, 1911. All right. So he destroyed. He actually replaced the atom model, his teacher's model, J.J. Thomson model, by his own model. So basically, he argues that the hydrogen atom or all atoms are made by nuclei. Okay? An electron is wobbling about the nucleus, occupy the most part of the atom. You see. So exactly what happened, they don't know. So probably the most reasonable guess is the solar system. So that is this is called the solar system model. So the solar system got this kind of the circles, like you can see. Got electron. So that's why in old day, many high-tech company use this logo. Government agent use this logo for atom. Can you see? So that's due to Rutherford. Rutherford. But however, if we accept the Rutherford's idea and following the Newton's law, so and also the Maxwell's law. So basically, if we consider the atom, if the atom is indeed made by a tiny nuclei with orbiting electron in the circle, can we just consider hydrogen now? Okay, if you have hydrogen now, then what happens is that if you put the electron here, can you see? So there's this electron, there's a proton, all right? And then if we assume this is doing circular motion, can you see the electron is orbit about the nuclei in the same way as Earth orbits about the sun, right? So this is a typical circular motion, isn't it? with the radius r, can you see?
Yeah.
Now, any force acting as a centripetal force, can you imagine?
The
Gravitational force.
Yeah.
Gravitational force, yes, that's possible. But unfortunately, gravitational too weak compared with another force. It's a Coulomb force. You see.
Mm-hmm.
What is Coulomb force? What is Coulomb law? Electrostatic force. Can you follow me? So this force, attractive force in the atom, in the hydrogen atom, can be represented by K multiply E squared divided by R squared. Original Coulomb's law is this. The original Coulomb's law, some textbook write this factor is called the 4 pi epsilon. Have you seen this factor? And Q1, Q2. In your formula sheet, did you see this formula sometime? This Coulomb's law. Have you seen Coulomb's law before?
Yeah.
Yeah. So that is an electrostatic force, all right, between the two charge. Because for the charge of proton and neutron, the charge is the same, you see. Although is one this proton, this electron, you see. So both have charge is E. So that's why this E squared, okay? Now, according to Newton's law, the centripetal, the circular motion at the circumference, there is a centripetal force was equal to MAC. Do you remember what is AC, circular motion? Centripetal acceleration?
Yeah.
V squared divided by something, what?
R.
Yes, okay. So if you combine these two formulas together, we will get K E squared divided by R squared. Can you see that? So if we simplify, we're going to use this formula. If we simplify this formula, can you see we can cancel this R squared, can you see? So in this way, we can simply write K E squared, you see, divided by R is equal to mv squared. Can you see that? From here to here, can you follow me?
Yeah.
Okay. And so this is very important formula. Can you see the formula 1, formula 2, formula 3? This is very important formula we're going to use. So Bohr is going to use this formula to build his theory. Yeah. But unfortunately, people realize that another theory is Maxwell's theory. So this is one is motion, right? So the first think of is Newton's second law. So Newton's second law. Another thing you have to consider is Maxwell's theory. So what is Maxwell's theory? Maxwell in the later 19th century rewrite the magnetism. So he just built the 4 equations. He got the 4 equations to describe everything. Okay, on electromagnetism, together and also electromagnetic wave. You see, he's the first person theoretically predict that the electromagnetic wave or light. You see. Photon, see, of course, nobody calls photon, and before the Planck, right? It's called the electromagnetic wave. So according to these Maxwell theory equations, and if the charge is doing acceleration, can you see? If the charge is with acceleration, can you see? This is acceleration, right? And if the charge is doing this like oscillation, can you see? They will emit energy, you see? So they will emit energy, So this energy is electromagnetic wave. So in other words, the energy of the charged particle will immediately decrease. All right. As a result, this, according to this classical Maxwell theory, the electron, the velocity will decrease. Can you see?
Mm-hmm.
And eventually, will just collapse. So what is called a collapse is that because they have charge, they probably neutralized by a new proton. Okay.
Yeah.
So that is the reason that classical physics cannot provide a proper explanation for the Rutherford solar system model. Now came to Bohr. Okay, Bohr got two assumption or postulation. First postulation is for Bohr is that you say they have the only stationary only stationary orbit are stable. Okay, exist only there's actually only these stations. Okay, that's very strange idea. He says that exist. So what are these orbitals straight? Well, he said, well, if this is the condition for this stationary orbit must satisfy this condition. So that's the first postulation. Let's just draw that. For the hydrogen, so if you put the proton in at the center, all right, and we can draw this so-called stationary orbit. So this time, you can draw one. They have different radius. So Bohr's model, one of the actually, should I say, the first objective, the prime objective is to work out the model for this radius of this so-called stationary orbit. You see, of course, nowadays in chemistry, people have taken for granted. Oh, that is okay. That makes sense because that's why they put the electron, you see, from the first, they call the shell, not called orbit. It's called the shell, right, in chemistry. Do you agree? And so that is the idea. So what happens that Bohr's clever is that say, well, if the electron jump, if there's some disturbance like a photon, electron can jump to one to another. Can you see? Or if not, this electron can also jump from here to here. It's all possible. Okay, and also they can come back as well. Can you see? They can come back. So we jump from the inner orbital to the outer orbital, and they will absorb energy. Can you see? So in this case, they have absorbed energy that's provided by external source, photon. Can you see? That is why. So if you do you remember the experiment? If you put a gas here, hydrogen gas here, so there are so many protons with different energy are available. Can you see? If the condition energy balance condition satisfies this condition, then the electron can jump and in the meantime absorb certain amount of water photon. So that is why this became black. Does that make sense now? So the absorption of each of these discrete, they call the line absorption. Each line of absorption is corresponding to two states. In this case, two orbit of atom, of hydrogen atom. These hydrogen atoms. We'll always talk about hydrogen atom. Atom. Can you follow me? Yeah. And to be exact, the proton is not moving, so we are actually talking about the electron. We are talking about electron, the state of electron. Okay. So in other words, according to his first assumption, that the atomic absorption spectra can be observed because the electron change their orbit, and of course, hence their energy. Can you follow me? So he has this, so therefore he got this famous formula that is, and the photon energy of photon is equal to the change between the two energy state of the hydrogen. Can you call the M and the N, or put other way around? Can you see? Does that make sense now?
Mm-hmm.
So if this is so this is one, this is another. So that is this is you can call it delta E if for short. Can you see? So that is a remarkable hypothesis. Okay, that is do you remember the photon? Do you remember the photon electrical effect?
Yeah.
And Einstein also used this formula. I write down here for comparison. Can you see? Einstein said the energy of photon can be transferred to the kinetic energy and plus work function. Can you see?
Mm-hmm.
Or you sometimes use W, right? Use W.
Yeah.
Okay, just as comparison. So both Einstein and Bohr accept the Planck's idea about photon. Okay, so photon, now radiation is not a wave anymore. Radiation is made by particles called the photons.
Mm-hmm.
Okay, so that is the first assumption. So that can avoid this called collapse with the unstable hydrogen unstable orbits in the Rutherford model. That is a first assumption. There's another one. There's another assumptions which also important but more strange. You can see, he argued that the postulation 2. He argued that, well, how do we determine this this called stationary orbit? See, how do we determine this? So this you can consider this Rn. Can you see?
Mm-hmm.
This R1, the nearest is R1. Now, how can we work out this formula? He said, well, the another is called do you know the angular momentum? Do you know the angular momentum? That is R multiplied P. So you can imagine if this is a P, this is V, right? So this is a V. If you multiply M, that will become P, which is a momentum, ordinary momentum, right? Now, if you just also multiply this R, that will become angular momentum. So this is the idea for the angular momentum. I write the name here, and angular momentum. Okay. He said angular momentum must be satisfy certain condition. Okay. If you rewrite this one, that can be written mv multiply r. Can you see? Because mv is p, right? So this is p. This is p. This angular momentum must be satisfy this condition. It's called n multiply h divided by 2 pi. So what is n? N is equal to 1, 2, 3 integer. Can you see? So this is known as this Bohr's. This second postulation is called the Bohr. So this condition, I will highlight this condition. So this condition is called the Bohr's quantum condition. Can write a few words here. It's called the Bohr's quantum condition. You may wonder where did this idea come from? Where did this idea come from? Are you interested?
Yeah.
Yeah, we'll talk about that. We're talking about, if we have time, we will talk about the de Broglie's wavelengths. Do you know did you discuss de Broglie's matter wave?
I think we discussed a little bit of it.
Yes, okay, but we will answer this question later. But Bohr is very clever. He wants to make his postulation is as original as possible. so that people would attribute, wouldn't attribute his work to someone else. You see, so he disguised his original idea by just putting this very strange condition. Okay, can we call this condition equation 4? You see that? Now we have two interesting equations. One is equation 3 we just derived. Can you see? Another is equation 4. And in equation 4, what is a hedge? Can you guess what is a hedge?
Planck's constant.
Planck constant, yes, that's right. So it's very clever. So he incorporated Planck constant in his hypothesis. Okay. Now, what's happened is this one is I will simplify the story now. And although this is not required in the ATAR, but I think it will be interesting to you, right? To know that this is a math and also the idea. If I just highlight this area, I'm going to talk about very important result of Bohr model, okay? So what we can do, we can just, we have mv squared here, can you see? So this m squared can also found in this formula. If we just multiply, if we multiply both sides with m, so if I just multiply, so from equation 4, if we multiply, we in order to get, can we say we got m squared, we can obtain m squared v squared. We just multiply this one, and other side will be nh divided by 2 pi r squared. Can you follow me? Okay, so this is similar to this formula, except there is only one m, right? There's only one m, so that's easy, because we can make this also as from the other side, as on the other side from this this time from 3, from equation 3, we can also got this term. Can you see? M squared v squared is equal to, we just multiply the m on both sides. That will become mk e squared divided by r. Can you see? Oh, can you see that? Now, if I just rewrite this as slightly different, can you see? This would be nh and 2 pi square and r square. Okay, can you see these two equations clearly? So if we solve, so these are the same now. Can you solve, use your algebra? Can you solve the formula for r based on these two equations? Then you got a Nobel Prize, but too late, 120 years later.
Are based on these two equations.
Yes. You see, the both equations, the left-hand side are identical. Can you see? These are identical. Good. Yes. Okay. Can you write your important discovery here?
Yeah.
Did you see R? Can you write the whole form result over here, this corner? That is the most important formula. R equal to, can you show this R? Wow, yes. M squared. Oh, you still keep the V square. Can we eliminate V? You see, these two equations is identical on their left-hand side. Therefore, their right-hand side must be equal. Do you agree?
Mm-hmm.
That is the way to go. That's the way to solve this puzzle. Sorry, you can try again. Good, good. Ah, you got the R on both sides. Square root. No. Can we go to next page? It's a bit crowded now. If I remember correctly, that is that's two equations: m squared v squared equal to, that is nh2 pi. Not nh, h has been provided. My memory is terrible. Oh, it's nh, yeah, nh over pi squared, yeah. nh over 2 pi square, right?
Mm-hmm.
Divide by r.
R squared.
R squared, yeah, by r squared as the first equation. The second equation is m squared v squared equal to k e squared, right?
Mm-hmm.
Divided by r, isn't it? Yes, or plus m, multiply m, multiply m. Okay, I can try again to solve these two equations. So objective is what is r? So formula for r, analytical formula. That's right. That's the right way to go. Wow. Right. Yes. Okay. Can we do something in which n is variable? When can be changed? Can you put everything in this bracket and just write n squared outside? What would be inside? That is the formula now. This is a Bohr's model formula. No, n has been removed. N squared has been moved. H squared, that's right. H squared, yeah. That's H squared. Can you write it in the fraction form, not the division symbol? One more step.
No, wait, it's the wrong way.
Yeah, you need just rewrite this replace this by fraction, that's all. Yeah. H square, yes, H square. Yep, that's right.
Mm-hmm.
Now, can we just rewrite this as A multiply n square? You see?
Mm-hmm.
Oh, something disappeared.
Oh, yeah.
Ke square, yeah. So this is called Bohr model, a Bohr radius, named after him, called the radius. That is the shortest radius or shortest distance from the nucleus. See. And by the way, do you remember what is the range of n? Integers.
Yeah.
1, 2, 3, and so on. You see? Even go to infinity. Okay. Of course, when n equal, you know that there's a there's some limitation for Bohr model that you have to bear in mind, that Bohr is trying to keep that Bohr trying to show that he had a formula for the circles, all right? But it turned out that there's another important quantity which is even more important than radius, which should be the energy. You see? E for energy, or the total energy, the total energy of electron in the hydrogen atom. Total energy of the electron. You see that? Because according to Bohr, so this formula is famous, but they're not much practical use. All right. Why is not practical use? When we do chemistry, we know that we draw this Bohr model in this way. Can you see? In chemistry, this is a nuclear, right? And the Bohr model, we just do this sketch the Bohr model in this way. Okay, this is 1, let me make it smaller, and then 2. Every textbook uses this model. Can you see? And of course, you can put the electron. Can you see? If I use the electron, I use yellow one. So 2. Can you see? How about the second share? You got 8, right?
Yeah.
You got 8. So that is a chemistry diagram. Can you see? However, if you use a Bohr model, if you draw this diagram, the diagram will be different. Can you see? I ask you from this formula. So from this formula, should I use this one? If I use this model, this is Bohr model. Can you see? According to Bohr model, Bohr the radius equal to A, the shortest. Oops. A is the shortest radius, A. So this is A, can you see? And n squared. So you can see n1 is equal to A, can you see? And R2, so R2 is equal to 4A, can you see? How about R equal to 3? How about R equal to 3?
R equal to 3 would be 9A.
Yes, 9A. Increase very fast, okay? So according to this Bohr formula, the Bohr model, so that this if that is a proton, can you see? So if this is a proton, you see. So if that is if I just use A, if you if we use a proper scale for the Bohr model, and that diagram will be look like this. So this is the first shell, can you see? And second shell getting 4 times like that, can you see? roughly, can you see?
Yeah.
And the last one will be like this, can you see? The third one will be something like this. Can you see that? Or even larger, because if this is 4, it's 9, it's even larger. Can you follow me?
Yeah.
So that is impossible, right? we run out of space very quickly. Can you see that?
Yeah.
So bear in mind, Bohr model has been used in chemistry, okay, very comfortably, right? When people were told the Bohr model, they use this chemistry model, it's chemical. In the chemistry's version. Chemistry is a Bohr model, okay? But actually this is real. So this is a real Bohr model. So this is a real Bohr model. Bohr model, you see? So it doesn't make much sense, do you agree? Because according to Bohr, as n increase, so that is n equal to 1 first shell, n equal to 2. Are you still learning chemistry?
Yes.
3, yeah. Can you see that? That doesn't make sense. So this is n equal to 1. That's n equal to 3. Can you see that? And how about the fourth one? 16, okay? So yeah. This is beyond this the whole screen. This proton. So that's something you have to bear in mind. So therefore, the Bohr model has not much use in physics, although it's useful in chemistry when we work out electron configurations, all right? So then we move to how do we determine more important formula for the energy. And with that formula energy, we can explain the absorption and the emission spectra of hydrogen atom. Okay. So just recap what we have obtained. First, we got one is Ke squared R equal to M squared, you see, MV squared, okay? And this is very important formula because if you just divide it by 2 on both sides, Ke, I just use some simple algebra, can you see? And that will become kinetic energy, can you see? MV squared. And if you just pay attention to amplitude, so this inside bracket will be the potential energy. Okay, and this side will equal to kinetic energy, or divided by 2. Can you see that? So have you studied the central field theory, the potential energy of the charge particle have you studied this formula? The potential energy can be written as K E squared. Of course, the general formula is the Q, okay? But we just use E squared here. Have you studied this formula before?
I don't think so.
Don't think so. But basically, it doesn't matter if you based on this two idea. Of course, this is EK. You know this is EK, right? So we can in this way we can alter the total energy. You see, so the total, that is what I'm looking for. Probably go to outside, right to R. From here we count the total energy of electron. The total energy. We are looking for this more important formula of the electron. Okay, in hydrogen atom. So, what is total energy by definition?
The potential energy?
No, the sum. The sum of these two, can you see? The sum of 2, all right?
Yeah.
Now, if we just substitute this formula here, the oh, sorry, there's no K, there's no square here. Okay. So if we substitute formula here, what is the EK? EK is equal to this one. EK, one moment. Yeah, EK is equal to Do you remember? Equal to the half half ke squared divided by r. Can you see?
Mm-hmm.
And the potential energy is negative. I forget about you. Remind you, they have always negative. For the potential energy for the electron, which is not free, or electron in the atom, their potential energy is always negative because the force is attraction. All right.
Mm-hmm.
Now, can you help me to simplify this sum? Can you see? What would be the sum? What would be the total energy for?
Negative ke squared over r.
Yeah, that's
half
right.
Squared.
Half with half, right?
Half.
Positive, negative, right?
Yeah.
Ke squared half r. Okay, that's good. So that is the total energy. Okay.
Mm-hmm.
Now, can we combine our formula? Can we combine the formula with Bohr's model? Bohr model say R equal to A n squared. Can we find the energy formula?
Negative ke
You can write
squared.
down. Can you write? If you can write, I can see it.
Mm-hmm.
That's it. Can you see? A is also a constant, right? A is constant.
Yeah.
Actually, if you use the proper unit, that En, we can put n here because the variable of is n. Okay, so n is equal to, as usual, is 1 as same as R n y 2 3 and so on. So energy, if you use a proper unit called the EV, electron voltage, that number is 13.6. Can you see? EV that divided by n squared. So that is the formula from Bohr's theory. You see? Okay.
Yeah.
Do you remember Bohr's first postulation? He said that can we just use this same page, or can we go to next page? Go to next page. I think too crowded. Yeah, I'm going to explain this absorption spectrum now, namely the Rydberg. Okay, Rydberg. So Rydberg equation. So we now know that for the electron, for the hydrogen atom, the total energy is simple, is equal to 13.6 divided by n squared. Okay, bear in mind that's in EV. On the other hand, according to Bohr, this says the energy of the photon is determined by the energy gap, a gap between the two energy. Okay, so that is determined by delta En. You see, we'll probably write this way. Can we just En take En? You see, yeah. N and M just different. Okay, the first equation, second equation, and the third equation would be the Rydberg's formula. Can you see? Can you follow me? That is m squared take and n squared. Can you see that?
Yeah.
Can you see now Bohr can explain this Rydberg's formula? So what is the formula for R? That's the question. Do you want to try? You can use this side. We got plenty of space here. Or before that, probably it would be helpful if I draw the energy diagram. Okay, that is how to draw the energy diagram for hydrogen atom. So this is ground state, lowest one. This is use purple color. This is lowest, okay, and it's n equal to 2, n equal to 3, n equal to 4, n equal to 5. Okay, you can derive your formula. I just draw this energy diagram for you. So that is En, hydrogen energy. Do we know lambda?
The wavelength?
Yeah. No, that is not the way. I show you, okay? I show you the right way to go. So basically, we just rewrite equation 2. So we just, because this can, H, can you see? HF can be rewritten as HC divided by lambda. Can you see that? So therefore, we multiply HC. So in this case, if we just multiply H, if I use the equation 2, so equation 2 will become that HC divided by lambda, okay? Will equal to, and negative 13.6 divided by m squared, minus negative 13, can you see? 13.6 divided by n squared, okay? Yeah. And then we will divide it. Can we divide the NH? Divide it, we got a lambda. Then we got a factor here, 13.6 divided by HC. That inside will become n squared, take m squared. If you compare this one, so this is our Rydberg constant. Can you see Rydberg constant?
Isn't it negative 13.6?
Yes, we have to, we'll fix that sign here, but first we just fix this result, okay? R is equal to 13.6 and HC. Can you see that? Doesn't matter. We can put this m here. Say we can m is because we have used m here. That's negative. Can I change the sign? Negative become positive. You see that? This is arbitrary. You can because here I use m notation and n equation is slightly different. So basically that is the explanation for Rydberg. And also with this new idea, with this new theory, the atomic absorption and emission spectra can be explained. That is the point. Do you agree?
Yeah.
Okay. See you next week.
Okay.
Yeah,
I'll see you next week.
Goodbye.
Thank you.
You are welcome. Goodbye.
Goodbye.
Goodbye.